43rd anniversary of the launch of Voyager 2, which was the first of these two missions to actually be launched. The Voyager program made use of, or I should say the Voyager missions imparted upon a grand tour of the solar system, especially Voyager 2. So when we say grand tour, what we're talking about is that especially like Voyager 2 didn't visit 1 or 2 planets, it actually was able to visit 4 planets, 2 of which we had never sent any probes to before. So this was a really big thing for NASA to pull off. One of the interesting facets of this is that there was a really big time constraint on being able to do this, because in order for a mission to be able to get from Jupiter to Saturn and then on out to Uranus and Neptune, that would require use of a planet's gravity to provide what are known as gravity assists. Otherwise, we might be able to get to 1 or 2 planets, but we wouldn't be able to get to the others. We just wouldn't have a mission that was powerful enough to be able to do that. It would require tremendous rockets, lots of cost, and it's really not feasible to do. So back in the 70s, when the program was being designed, they were making use of an alignment that occurs about every 175 years with the outer planets in our solar system. That's Jupiter through Neptune. And so in this diagram here, you can see that we have Earth as the little blue circle orbiting our sun right in the very center there. Green is Jupiter. This teal color is Saturn. The yellow planet is Uranus, and then the orange one is Neptune. And you can see that in this kind of purple or kind of pinkish purple tone, this is the Voyager 2 mission. So you see that we launched Voyager 2 back in 1977 at just the right time to where it would intercept Jupiter. Jupiter would essentially, in a way, kind of fling it over to Saturn. Saturn would then do the same to get Voyager 2 over to Uranus. And then Uranus would do us a favor and do the same thing to get us over to Neptune. And then after that, Voyager 2 started to leave the solar system, or was making its way out of the solar system. So again, this happens about every 175 years, so NASA was able to get everything completed in time so that we can make use of all these gravity assists. And we'll talk some more about that in just a bit. Here is a model of Voyagers 1 and 2. So they were twin spacecraft. To give you an idea of size here, one of the main topics of our talk tonight is our golden record, pictured right here, kind of on the belly of the spacecraft. That's right at 12 inches or 1 foot in diameter. So this will give you an idea of just how big these craft are. I'm going to pull up just a few labels, but for sake of time, I'm not going to go through everything here. But I will point out 1 or 2 interesting things here. You'll notice that unlike a lot of the missions that NASA or the European Space Agency sends out, we don't see solar panels on here, because once we start getting out into the far reaches of the solar system, especially around Uranus and Neptune, we're so far away from the sun that the sun is much dimmer, and solar panels are really not going to be effective. So I just wanted to point out this little device over here called the RTG, which stands for the radioisotope thermoelectric generator. This was essentially a nuclear-powered craft. So there was plutonium-238 in here, which as it decays over time into other elements, that releases heat. And a thermoelectric generator can take heat and convert that into electric power. And so there was no need for solar panels on here. The RTG would provide power for a number of years, but over time that power dwindles, and eventually we won't be able to communicate any longer with the craft. So as I mentioned before, today is the 43rd anniversary of the launch of Voyager 2, launched on August 20th, 1977. And you'll notice that Voyager 1 actually left after Voyager 2. It was launched about 15 days after Voyager 2. Voyager 1 would end up getting to the first targets before Voyager 2 because it was launched at a higher velocity and more or less on a more direct course. Or we'll say that Voyager 2's journey out into the solar system was a little bit more circular course, but that allowed Voyager 1 to overtake it and get to our first target, which was Jupiter. And we'll talk about why that is in just a moment. So the missions of Voyager 1, there were 3 primary goals. One was to do a flyby of the Jupiter system. As you see here, it passes by Jupiter and gets a gravity assist, taking observations of the planet as it goes. And then once it gets to Saturn, it does a flyby of Saturn. And then once it starts to leave the Saturn system, that's basically the end of its mission. So it was to study the Jupiter system. It was to study Saturn, its rings, some of its moons. But the third objective was to really study one of those moons more closely by doing a closer flyby of it. That moon is called Titan, and it's of interest for astronomers because it's the only moon in the solar system to have an atmosphere. So they wanted to get more information about this moon. You know, why does it have an atmosphere? How is it able to retain that atmosphere? What are the conditions like? And things like that. So the whole idea for Voyager 1 was that it would go to Jupiter first, then Saturn, and then be on a trajectory as it's going into the Saturn system so that it would not only fly by the planet, but it would be able to do a flyby of Titan. If something were to go awry along the way, let's say it could make mid-course corrections to where it could do a flyby of Saturn, the idea was that Voyager 2, which would be following it by a few months, would then make a course correction on its way to Saturn and would divert its course just slightly so that it could pass by Saturn, but also do a flyby of the moon and complete Voyager 1's mission. Unfortunately, though, that would mean that if it had to fly by, do the flyby of Titan, that Voyager 2 would not be able to then go on to Uranus and Neptune. It just would not be able to achieve the necessary trajectory. So let's just do a couple of results from the Voyager 1 mission and Voyager 2 mission, and then we'll talk about the records. So Voyager 1 reached Jupiter in the first part of 1979. It began taking photos in January and made its closest approach in March of that year, and then continued taking photos of the system until about April or so, getting about 19,000 images total before it finally ended its Jupiter phase and was waiting to get to Saturn. So here we have a really nice montage of images of the Jupiter system. We've got Jupiter in the background, showing a lot of details in the clouds, including the great red spot here. And then its 4 largest moons, which are easily visible through a backyard telescope. Now again, this isn't a single image. These are actually individual images of each of these moons, individual color images that have then been combined with the image of Jupiter to kind of give a family portrait, if you will. So one of the big discoveries at Jupiter was that Jupiter had rings. They were minuscule in comparison to Saturn's rings, but nevertheless, the planet did have rings. The top image is a color composite image, and you can see that very thin ring, which was imaged as Voyager 1 was behind Jupiter in its shadow. Below, you see the original discovery image of that. These jagged things here, these are actually star trails. So as the craft is moving and making adjustments, the background stars appear to streak a little bit as it's trying to stay focused on its much closer target, which was the rings there. So just kind of ignore those little jagged artifacts in there or objects in the image. But it looks like, or what Voyager 1 helped us see, was that these rings actually coincide with the orbits of some of the very smaller inner moons of Jupiter, much smaller than those previous moons that we were looking at. And one of the other major discoveries, which really surprised a lot of people, was that the innermost of those 4 large moons, it's called Io, easiest moon to spell in the solar system. It is the most volcanically active body in the entire solar system. And we're including the Earth in that. We're including all the volcanoes that are active right now. It is the most volcanically active body in the solar system. As Voyager 1 passed by and got some really nice views of its entire surface here, which, by the way, this is about, I'd say 25% wider than our own moon, so comparable in size. But as it was taking images on the flyby, it did catch images of an eruptive plume here. Now in this image, it has been enhanced to where we can see that plume a little bit better because it would have actually been much fainter. But nevertheless, we are seeing active volcanism on a moon in the solar system. And moons should have been, as we say, geologically dead. They should not be doing this kind of stuff. So that was a big surprise. And since then, we've imaged these eruptions even more from other probes. So then on to Saturn, about a year later, thanks to the gravity assist of Jupiter, Voyager 1 arrived at Saturn. This is another nice family portrait here. Again, individual images combined into a single image. The moon that looks pretty small in here in this upper right, that is actually the moon Titan. That is one of the big targets for Voyager 1. In front of us here, in this nice closer-up view, we have the moon Dione. Over here is Enceladus, which we now know has ice geysers on it. This is Rhea, Tethys, and the moon Mimas, which we'll talk about in just a second. But getting a good flyby of Saturn, Voyager 1 was able to image the rings very well, and it was shown that the rings are basically not this big plane of material that's just orbiting around Saturn. It's actually organized into thousands of individual ringlets that are all in orbit around Saturn. So they lie in a very, very thin plane. The rings are about 180,000 miles wide, but they're less than a mile thick. So when we talk about they're really organized, they are really organized. We discovered another ring, which we couldn't see from the Earth. And we also discovered that there were these things called shepherd moons. So this ring down here, this thinner one, this is called the F ring. And there's an A, B, C, D, E, and F, and now a G ring. They're labeled in order of their discovery. But the F ring, which was the last ring to be discovered before Voyager 1 got to Saturn, it was then found to have what are known as little shepherd moons that are basically in orbit right next to the ring. And the gravity of the shepherd moons helps to keep the material in that ring kind of tightly packed in so that the ring essentially doesn't disperse and become part of the rest of the ring system, but it keeps it very nice and neat there. So in doing the flybys of the system and getting some more up-close images of the moon, we got a good view of the moon Mimas. If you're a Star Wars fan, then you immediately probably thought this looks exactly like the Death Star. And you probably thought, I wonder if George Lucas got his idea for the Death Star from this moon. So it turns out this image was taken 2 years after the first Star Wars movie came out. So it just happens to be a coincidence. But this is a very large impact crater on this moon. And it's theorized that if the impactor were a little bit bigger than the one that created this moon, if that impactor had hit this moon, it would probably have shattered it. So, which FYI, the little black area and these little 2 white dots, those are just artifacts. So they're not actually there. Okay. But with Titan, Voyager 1 was successful in getting a flyby of the moon Titan. And it was found that Titan's atmosphere, which was much, much thicker than previously thought. We'd known that Titan had had an atmosphere for about 30 years, but we didn't know many of the details of it. And so the atmosphere was so thick that we couldn't even see some of the surface features of it. In fact, you can't even use just a regular camera on one of these probes to see the surface features. You have to have a special type of camera. But it also discovered that the atmosphere is mostly nitrogen, and it even has haze layers and different layers of the atmosphere. So we won't have time to go into all of those, but these are just some of the highlights. So Voyager 2, it was going to follow in the footsteps of its twin, Voyager 1. It's going to do a flyby of Jupiter, study as much as it could during that period of time, do the same thing with Saturn. Thankfully, since Voyager 1 was able to do a flyby of Titan, Voyager 2's trajectory did not need to be altered, and so once it did a flyby of the Saturn system, it could do a gravity assist to then head on out to Uranus and then Neptune to give us our very first up-close look of these 2 ice giant planets. So here, this was the first graphic that we showed at the beginning of the talk. So Voyager 2 really embarked on the grand tour. So it not only got to see what Voyager 1 saw, but it was going to get 2 bonus planets as well. And so just like with Jupiter and Saturn, its goals was to, to study as much as it possibly could, because it wasn't going into orbit around these planets. It was basically flying by, snapping images, taking as many readings from its various instruments as it possibly could before it left the system. So Voyager 2 encountered Jupiter a few months after Voyager 1. And with the discoveries of Voyager 1, we got additional images, including the ring system, the plumes coming off of Io, and we even got a nice mosaic of part of one of those 4 large moons. This one's called Europa. And previous images had hinted at a surface of this moon that was very fractured, like it was very geologically active. And it looked like maybe it was covered in ice. So the thought was that maybe this is an ice-covered world that is that ice layer is floating on a liquid ocean. And so this has been a real interest for astronomers, especially astrobiologists, because here on Earth, wherever we find life, we find water. And so this might be a potentially great place to search for life in the solar system one day. So then we move on about a year later, and we encounter, Voyager 2 encounters Saturn. We do the same thing as Voyager 1, try to get as many images of the moons, study the rings as best we can. Voyager 2 got a few other images of moons that Voyager 1 wasn't able to see. Down here at the bottom left, we have Hyperion. This one is Iapetus, and then this one is Calypso. And you notice that some of these moons are very irregular shaped because they're likely captured asteroids. Voyager 2 also noticed these dark features in the rings that moved with the magnetic field of the planet itself. And those were referred to as spokes. It's now thought that these are basically clouds of very fine dust that are interacting with the magnetic field of Saturn. So after that, about 5 years later, we get Voyager 2 at Uranus. And this is the first time that we've ever seen this planet up close. And, to kind of be frank, Uranus was remarkably unremarkable when we first looked at it. You can do some color enhancement and other enhancements on this image and start to bring out some very fine clouds. But when you compare this planet to, say, Jupiter or to Saturn here, you can see that even Saturn has some distinguishing features in its atmosphere. But Uranus was, like I say, remarkably unremarkable, which was a big surprise for people. As Voyager 2 flew by, it was able to get readings of the magnetic field of Uranus. And there were a couple of surprises there. One, the magnetic field is tilted quite a bit with respect to the rotation axis of the planet. So the Earth's magnetic field is tilted a little bit with respect to its rotation axis, but not nearly as much as Uranus's magnetic field. And not only that, but the entire magnetic field seems to be centered in an area about a third of the way down from the center of the planet. So we're not really sure what causes that. But there's also evidence that based on, for example, the density of the planet, given its mass and size, we can get an idea of the density and have an idea if it's solid or if it's just a big ball of gas or maybe it's got ices. There was strong evidence from the data that suggested that there was an ocean that started about 500 miles below the cloud tops of Uranus. And then finally, we were able to watch some features and get some wind speeds. And like its other cousins, Jupiter and Saturn, Uranus does have high winds. Those planets all have high rotation rates. They take less than an Earth day to rotate. So it wasn't a big surprise that Uranus also had some high winds. But on its trip through the Uranus system, we were able to discover 11 additional moons we didn't know about. We were able to image some of the few moons that we did know about. And for example, here are, up here at the top left is Oberon, then Umbriel, then Titania, and then Miranda. If you note, if you're a Shakespeare fan, then you'll note some of those names, or all of those names are actually characters from the works of Shakespeare, and actually Alexander Pope as well. We also discovered a couple of additional rings as well. So some of the rings had been known for about a decade, and then Voyager was able to image those and then get images that showed a few other rings, bringing the total up to about 11 rings now. And then finally, about 3 years after its encounter with Uranus, Voyager reaches Neptune, which was the last stop on the mission leg of its journey anyway. So after having seen Uranus and finding how very unremarkable its surface was, astronomers were really wondering if we would see the same thing for Neptune. We didn't. We actually saw some other features. So for example, and this is a little bit of a color enhanced view here, there were several atmospheric features. The most famous is this area here called the Great Dark Spot, which is kind of an analog in a way to Jupiter's Great Red Spot here. This spot on Jupiter is actually a very large storm that's been going on for at least a couple of centuries. On Neptune, however, this dark spot is not really a storm. It was originally thought that it might be a storm, but now it appears that it's essentially kind of, for more more or less a hole in the atmosphere of Neptune. So we're looking down a little bit deeper into the atmosphere than, say, over in this area. There were other features like what we call the little dark spot, or some people colloquially call it the wizard's eye. This was a storm system down here. And there were some white cirrus clouds like we see here and here. And one of them was even nicknamed Scooter, because as we watched Neptune orbit, or excuse me, as we watched Neptune rotate, as Voyager 2 was approaching it, we saw that this little Scooter feature was actually moving faster than features like the Great Dark Spot. So it was given that fun little name in reference to its high velocity. It had even higher winds, about 680 miles per hour. Even stronger winds have been measured since then. One of the windiest places in the solar system. It also had a very offset magnetic field like Uranus. Wasn't tilted quite as much as Uranus, but it was shifted even farther south to the South Pole, about halfway down to the planet. And again, that's still a big topic of research as to why that is. So in all, we discover 6 additional moons orbiting Neptune. We're able to image the 2 known moons, or the moons that were known at the time. 4 additional rings were discovered, and there had been suspicion of these things called ring arcs, which we see in this photo here. You can see how this part of the ring looks a little bit thicker. That's one of those ring arcs. It's basically a little clumpier area of the ring. And there's still a lot of work being done to try to figure out how that's possible, because according to what we know about the rings, they should basically, the material should distribute evenly in the rings. So finding these clumps was a big surprise and still a topic of research. So for the mission phase, I'll end with this particular picture. I really like this view. This is shortly after Voyager 2 made a pass over the North Pole of Neptune and starting to make its way out of the solar system. So this is like a parting shot of Neptune and its largest moon, Triton, which by comparison, this moon is a little bit larger, or excuse me, a little bit smaller than our own moon. But anyway, it's a really kind of a just very beautiful image. I want to switch gears for just a moment and mention this gentleman, Dr. Carl Sagan. If you are a fan of the Cosmos series, especially the original Cosmos series, then you're very well aware of Dr. Sagan. So he was an astronomer, a cosmologist, a writer, a science communicator. He did just a little bit of everything, and he was really good at what he did. He was especially good at communicating science and really getting people to understand and appreciate what they were seeing or what they were learning. He was heavily involved in the Golden Records, which we'll start talking about in just a moment. But his involvement in a project like this actually didn't start with the Voyager missions. It actually started with the Pioneer missions, Pioneer 10 and 11. So Pioneer 10 and 11 were launched a few years before the Voyager missions, and their mission were to travel to Jupiter and Saturn, get some of the very first up-close views, and really get a sense of what the environment was around these planets. For example, we knew that Jupiter had a strong magnetic field, which might lead to very high levels of radiation. So we needed to get a sense of just how strong that radiation was, so that if we send additional probes, we can make sure that they're built to withstand that environment. So before they were launched, Dr. Sagan was approached by Eric Burgess, who was a journalist, and had this idea for essentially sending a little, basically a little plaque or a little token of our existence along with these missions. And so pictured here on the left, we have a model of the Pioneer missions. And on the right is a photo of Dr. Sagan holding one of the plaques that would be mounted to one of the Pioneer missions. And so on it, it's kind of an analog of the Golden Records that we'll be talking about shortly. On it, we'll see that pulsar map that was mentioned at the very beginning in the introduction, which gives folks, or I should say folks, but extraterrestrials who find this an idea of where we're located, where this probe came from. As a depiction of us, an outline of male and female against an outline of the probe to kind of give whoever finds this an idea of, essentially how big we were, okay? And then at the bottom, there is a depiction of our solar system with the sun right over here and the planets in a line, showing a line coming from the third planet, Earth, and pointing up to the Voyager craft, or excuse me, the Pioneer mission to show exactly where we came from. So having done this, and the Pioneer missions were launched, Sagan was part of, or he was actually the chair of the committee that would then work on the content for the Golden Records. So before we switch to that, I want to show one other thing. In 1990, so we'd already passed Neptune with Voyager 2. Voyager 1 was even farther out in the solar system, well past the orbit of Neptune. Dr. Sagan had the idea of basically getting a family portrait of our solar system because no probe had ever taken an image from that far out in our solar system. So at the time, Voyager 1's cameras and a lot of the other instruments were already shut down to help conserve power and leave power for remaining instruments that would be useful well out into the depths of space. But he convinced the program directors to essentially turn the camera on Voyager 1, redirect it back towards the solar system, and then take an image or take multiple images to try to get basically a family portrait of our solar system. And so this is the final result here. You'll see if you download the high resolution version, it works a lot better than what I'm showing you now. But you'll see in this view here, we've got the letter J for Jupiter, and there'd be a little spot there. E and V for Earth and Venus. Saturn's right over here. Uranus is right over here. Neptune's right over here. In fact, we even have insets of those 6 planets to where you can see that, at that distance, even Jupiter is like a little dot. Okay. Mercury was lost in the glare of the sun, so we couldn't see it. And Mars happened to be on the same side of the sun as the Voyager 1 mission. So we were essentially looking at the night side, so you wouldn't be able to see it anyway. But anyway, this is a really great family portrait. This year marked the 30th anniversary of the release of this solar system family portrait. And so in commemoration of that, the image containing the Earth was reprocessed. And so we see it here. So this little dot right in the very center, that is our planet. And you can see it's caught in this light area. That's actually just a little bit of scattered sunlight. So that's not a real thing there. It's kind of like the glare from the sun. But nevertheless, that little bitty dot is our planet. And I really like this quote from Dr. Sagan that addresses this family portrait. And this is just part of it. But like I said before, he had a real knack for being able to speak eloquently and really evoke emotion and looking at things like this. So I love that he said, look again at that dot. That's here, that's home, and that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. And so, just really seeing this photo here really kind of evokes to me, just how small we are in this great universe. We're just looking at a very tiny fraction of our solar system, and already our Earth looks so small. So it's really kind of a very dramatic image. So I encourage you all to go and look at the original family portrait if you get time. So to end with the mission part, where are the Voyager missions now? Well, so in this diagram here, we have our sun with the planets orbiting around it, and surrounding our sun is what we call the heliosphere. Okay, just to kind of ignore this darker blue area for now. Okay, but the sun is constantly streaming particles away from it. It's what we call the solar wind. That stuff interacts with our atmosphere and our magnetic field, and it helps to create the northern and southern lights. They're basically just protons and electrons. But that solar wind goes well past the Earth, goes well past Neptune. And so wherever that solar wind is moving out, we call that the heliosphere. That's basically the sun's influence. So eventually there's a point where as our whole solar system is moving through the galaxy, and we're moving through very fine amounts of gas and dust in our galaxy, that bubble that we're in, that heliosphere, is pushing against all that material. And as we start getting to the edge of the heliosphere, then the bubble isn't able to exert as much force on the interstellar material. And so eventually what we should see is that the solar wind basically stops at a certain point because it can't exert enough pressure to to escape any farther away from the sun. So that's what astronomers are defining as the heliopause. So that's basically the limit of the sun's influence. And so if we pass the heliopause, then we basically say that we're out in interstellar space. We're no longer essentially part of the solar system. So this is a schematic kind of showing how Voyager 1 and Voyager 2 have both left the heliopause. So they are now out in interstellar space and have begun their interstellar mission. So there are still a few instruments on, essentially the particle detectors that can detect these high energy electrons and protons coming in from the depths of space. So just to give you an idea of how we know that they've left, here are the readouts of from the Voyager 1 mission. So this starts out in October of 2011 and it goes until December 2012. On the left graph, you see a readout of the amount of particles essentially coming from the sun that it's reading. Okay, so in these areas where we've got about 30 particles per second, that's basically 30 particles from the sun are hitting the craft and it's able to detect that. But once we get out to about August, all of a sudden that diminishes extraordinarily fast and basically goes down to about 1 particle. Okay, so this definite drop is a good sign that we've left the heliosphere. We've crossed that heliopause. And then finally over here on the right, this is a graph of the higher energy particles coming from the depths of space. And so you see it around the same time we get this big drop, we start getting a surge in our particles coming in from outside the solar system. So this is how astronomers can say, yes, we've left the solar system now with Voyager 1 and 2. So a little bit after that, I forget exactly how long, but Voyager 2 also registered the same thing. So they have essentially left our solar system. Now, the golden records. Let's talk a little bit about what's on the records and how we hope that aliens that find these will be able to decipher all the hard work that's been put into these to figure out, who we were, and things like that. So on the right side is an example of one of the golden records. This is actually a 12-inch copper disc that has been etched with the appropriate grooving, which contains the data, and has been gold-plated. It's actually double-sided, so that we can get essentially double the playing time, like a record, a normal vinyl record, except that it's not vinyl, it's gold-plated copper. And then on the left over here, we have the cover that goes over the record to help protect it from things like micrometeorites, or helps to shield it from radiation from the depths of space, like those cosmic particles coming in. And we're going to be focusing most of the rest of the talk on this cover. How are aliens going to be able to figure out how to get to this data? Okay. So what's on the records? As we've mentioned at the intro, there are a number of different things on there, including a message from the Secretary General of the United Nations at the time. There are greetings in 55 languages. There are sounds of the earth. Just a few of those to name are, for example, the songs of whales, a thunderstorm, a heartbeat, laughter. There's even like the Saturn V rocket, which took astronauts to the moon multiple times. There's even the sound of one of those launches. There's also about 90 minutes of music from essentially all over the globe. So we've got anywhere from Mozart to Aboriginal songs. So we really kind of get a little sampling of as much as we possibly can. So it makes sense that there would be a lot of sounds on there, and given what we know about how we've played records in the past, putting them on a little turntable with the needle will generate the signal to create audio. So that's not the big issue. The big issue, and even in the creation of these records, was figuring out how do we get images onto a record like this. So at the time, we didn't have the technology to generate like JPEGs and put it on a little thumb drive or put it on a CD and encode these images. We had to use the technology at the time, which was the mid to late 70s. So as mentioned in the intro, the images have actually been encoded as sounds, and a lot of the instructions on the covers of the golden records are telling you how to take those sounds and convert those back into images. Okay. So here are the golden records being mounted onto one of the Voyager missions. And then We have on the right side here, this is John Cassani, who was the project manager for Voyager back in 1977. He's holding up a flag, which was later folded up and sewn into the thermal blanket of Voyager 2 here, but this is the record and the cover that was going to be mounted to Voyager before, in this case, Voyager 2 before it was launched in 1977. So the record cover, just a very quick snippet of intro, and then we'll go into some of the details. So it's made out of aluminum. It is inscribed with a series of symbols and illustrations that will provide instructions on how to access the information on the record, specifically how to take the sound and convert some of that information back into images. And it also contains information about how to figure out where this probe actually came from. And we can't really see it here, but electroplated onto the cover is a small spot of ultra-pure uranium-238, which is a radioactive material that decays into other elements. Namely, the final product is lead-206. But the point here is that uranium decays at a known rate. And as we'll talk about at the end of this talk, if you look at how much of your original sample you have versus how much of the decay product you have, you can determine how long that sample has been there, and thus how long this probe has been in space, or how long it's been since it's been launched. All right, so let's get into some of the nitty-gritty details here of how astronomers and developers of this golden record were hoping that extraterrestrials would figure out how to interpret the data. So we're going to start down at the bottom right of the cover here. So I'm going to zoom in just a little bit. We're going to start with this symbol, which was also located on the Pioneer 10 and Pioneer 11 plaques that Sagan helped design. So what we're seeing here seems to be a very cryptic symbol, but this is actually the key to interpreting the rest of the instructions here. So what we're seeing is a depiction, a pictorial depiction of the behavior of the hydrogen atom. So what we've got is a hydrogen atom over here, okay? So hydrogen, the simplest form of hydrogen, has one proton at its nucleus and one electron orbiting that nucleus. It's the simplest element in the universe, and it's also the most abundant element in the universe. So any extraterrestrials ought to be aware of its existence. So here we see one hydrogen atom, and we see it in one energy state. Now compare it to this one over here. It looks almost the same, except that our symbol here representing our electron, it has turned right side up. What this is hoping to say is that this is basically a before, and this is an after. And there's a line that's trying to depict that, okay? Underneath that line is a 1. And this 1 is basically trying to signify the time that it takes the hydrogen atom to go from this state to this state, okay? This is known as the hyperfine transition of hydrogen, okay? It is an incredibly short amount of time. It is, here's the value right down here, it's basically about 0.7 billionths of a second. Okay. Now the whole reason that we're using this hydrogen atom is because we need to provide instructions in something that any extraterrestrial would likely have access to or likely have seen. If we use our own numbers, like the Arabic numbers down here, like that 7.04, it's very unlikely that any extraterrestrial civilization is going to be using those same types of symbols and know what they mean. So we need to go to something more primitive and simpler that we can express these values in. So anyway, this very, very tiny number is represented by 1, okay? So the time it takes the atom to go from here to here that's 0.7 billionths of a second, okay? So here's just kind of a depiction of what we're seeing here to make it a little bit easier. So the hydrogen atom has the proton in the nucleus, the electron orbiting, and particles like protons and electrons have a number of different properties, one of which we call spin. And it's, for depiction purposes, it's actually a very easy thing to depict, in that the proton or the electron can either have a spin up or a spin down. Okay, we're not going to talk about exactly what the spin is relating to, but just know that these particles can either be in a spin up or a spin down state. When they're like this, in this state where one is up, one is down, that is a slightly higher energy state than over here, where we have both particles either spin up or spin down. So when a hydrogen atom transitions from this state over to this state in that 0.7 billionths of a second, it releases a tiny little bit of energy. In fact, the energy is so small that it comes out in the form of radio waves or radio light. Okay? This particular type of radio light permeates the galaxy, it permeates the universe. In fact, astronomers use it extensively because it's often very easy to observe when other types of light aren't able to be observed. Just as an example, here's our Milky Way taken in visible light, the kind of light that your eyes can see. So this is an all-sky view, and you can see all the stars, lots of stars down in here, not so many down over here. But here's our galaxy going through the center. So this is visible light, what your eye can see. Let's look at the same area, but in that light that hydrogen will emit when it goes through that hyperfine transition. As you can see, there's not a little bit of that light, there's a lot of that light. Okay? In fact, these are two galaxies down that appear below our galaxy. They're called the Magellanic Clouds. But the point here is that this radio light, it permeates through dust and gas very well. So extraterrestrials should be able to pick it up. Even if they're in very dusty regions in space or very gassy regions in space. So to circle back and put in summary here, this little one is basically representing the time to undergo this transition, which again is that 7.04 times 10 to the minus 10 seconds, or that a 7 billionth or 0.7 billionth of a second. We're going to keep referring to that number, so just kind of put that in the back of your mind for now. So now the key to then using that to figure out all of the rest is binary language. Okay, you probably have heard of binary language, especially when dealing with computers, because even though we might write code using words and numbers and symbols, the computer, in order for a computer to run that, it then has to be translated into ones and zeros, which is binary. And binary means two, so there's the one or the zero, the two symbols here. Converting our information into binary is likely going to be the most easily understood version of this information because it's the simplest. It doesn't make use of 10 characters like our numerical system makes use of, 0 through 9. It makes use of 2. So if we can express all of those other values in terms of those 2, okay? So the way this works is we can take a value like, let's say 967, and we can convert that into a sequence of ones and zeros. And to do that, we have to do, basically have to do this last step here. So in a binary sequence of ones and zeros, every digit represents 2 to a certain value, then multiplied by 1 or 0. This probably, if you're not used to working with binary, that may have gone right over your head. And it's kind of a very ambiguous sentence. So let's actually delve into that and give some examples, because it's a very neat way of expressing things. So let's imagine that we have this binary value here. So it's 1001. So if I were to write that down and say, okay, what number am I trying to represent here? Using a little knowledge about binary system or binary numbers, we can then convert that into an actual decimal value like 7 or 14 or 9 or whatever. So, like I mentioned before, each of these numbers, each of these ones and zeros represents a position. So we start at the right and we start numbering to the left. So this one is at position 0, this one's at position 1, this is at position 2, this is at position 3. Now in that last sentence from the previous slide, we want to take that position value, or this position, and raise 2 to that position, as I've done here. So here's my 0, I'm raising 2 to that 0. For this one, I'm raising 2 to that 1. Here I'm raising 2 to the 2, so on and so forth. Okay. If I had another, let's say 1 out here, then I'd have a 4 right here, and that value would be represented by 2 to the 4th, okay? Now, what is 2 to the 3rd or 2 to the 2 or whatever? So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3rd is 8, okay? So this is ultimately, I'm laying out a bunch of steps here. I don't want to jump too many steps. So basically what I wanted to figure out is, what is each one of these numbers up here trying to represent? This 1 is representing the 1. This 0 is representing the 2. This 0 represents the 4. This 1 represents the 8, okay? So I've got those values. So now what do I do? Well, there's 2 steps. Now take these values which they represent and multiply them by either the 1 or the 0. So this one represents 1, and I multiply by 1, so I get 1. This digit represents 2. I multiply it by the 0, I get 0. This represents 4. I multiply by 0, I get the 0. This one represents 8. I multiply by 1, and I get 8. So ultimately, this is the second to last step. Final thing, all I do is now add up all of those numbers. So 8 plus 0 plus 0 plus 1 is simply 9. So if I were to write this down on a piece of paper and say, what digit am I trying to represent? You could do these steps and you get the number 9, okay? So this may seem like, you know, might make your head explode, especially if you have to deal with, let's say, 10 digits. You know, it certainly make mine explode, and I would get very tired of doing this. But this is the basis of how we're expressing all of these different values and all of this other information. So if our ET friends are able to understand binary, then they're going to be able to decode the rest of this information. So let's take this knowledge now and apply it. We'll do one more example here, just so you can kind of get an idea. So here's a little bit longer string. I'm going to do the exact same thing that I did before. All of these are representing individual positions. I raise 2 to the position values, calculate what those are. So here's my original 1, 2, 4, 8. Next one's 16, next one's 32, so on and so forth. So the next one out here would be 512. Next one after that is 1024. And so you use however many of those digits you need in order to create your number. So just to clean this up a little bit, so this 1 represents 256, just like we did before, and the 0 represents 128. I go through, do the calculations, add them all up. So this particular string of 1s and 0s represents 361, okay? So if I were to write out this value here, then I could do the conversion and figure out, hey, that actually represents the number 361, okay? Now, let's say I had that written, let's say that number was on the record or was on the cover, and say, well, what is the 361 referring to? Well, remember, when we were first talking about binary, we were talking about this, this transition time. So that 361, if that's on my record cover, that's saying 361 of those transitions of hydrogen. So since each one of those transitions of hydrogen represents this amount of time, I multiply by 361, and that'll tell me a certain length of time that's pertinent to whatever I happen to be looking at. And we'll see that in action in just a moment, okay? So we've done a little bit of binary, and now we know whatever our binary code translates into, whether it's 361 or 8 or whatever, we then have to multiply it by that transition time, okay? And then we'll get something meaningful out of it. All right. So we've spoken about this little area down here, which again is kind of like our Rosetta Stone for the rest of this. Now let's look at some of the other things. All right, so this is a top-down view of our record. And just like with a regular record player, there was a little cartridge that had your needle on it. That would then be placed on the record, and as the record rotates, the needle vibrates in the groove and generates the signal that you would hear as, for example, a sound, okay? So this is first showing ET how to place the cartridge. It's not going to be placed in the center here. It's not going to be placed at the edge or the inner edge. We're going to place it at the outer edge. Also note that there is this 1 here. This actually represents a 0. This is a 0. This is a 1. This is a 1. So this, all of this around here, these aren't little decorations. This is actually a very long binary number, okay? this is telling us how to set up this record for playback. Okay, so first, again, it's showing us our cartridge and our needle. It's the top-down view showing where to place that cartridge. And around it is that very long binary number. So this is the actual number here. I think there are 34 digits. You go through that conversion, it corresponds to this value. And you say, well, why do I need that value? Remember, we've got to multiply it now by our hydrogen transition time, which was this number down here. So when you do that, you get a very nice number of 3.6. What this is saying, and the reason that it's wrapped around here, is saying that once you have this record set up correctly, you will need to have it rotating every 3.6 seconds. Okay, or in other words, it will spin 16 2/3 times every minute. So that will set the correct playback speed. Okay, so we got our top-down view, but do we hold it the needle really high above it? Do we put it right in contact with the record? What do we do? So underneath of that top-down view is the elevation view. So now we're looking at the record from the side. So now we can definitely see, okay, we're still at the outer edge. We've got our needle just touching the edge of that record. These little marks represent the center of the record and the outer edge of the record. So what is that telling us now? Well, this is a little bit of not as critical information, but if we take that binary digit, which actually this one is the 34 digits, and we convert this long string of digits into decimal, we get this value. Again, we multiply it by our transition time, and we get about 3229.4, which equates to about 53.8 minutes. It's basically telling us how long it will take the record or the stylus to move all the way to the end and finish playing if that record is rotating every 3.6 seconds. Okay, so it's kind of like a backup bit of information for ET to make sure that things are being played correctly. So they can convert that 3229 seconds to whatever time unit they use, and they'll be able to tell if they're running things correctly. Okay. So now here comes the more, this is the more in-depth one. Now we figured out how we're going to play our record. We know how to set the stylus on there. We know how fast it needs to rotate. We'll probably hear some sounds coming out of it. But what do we do with some of those sounds? Some of them are going to sound pretty harsh to your ear, which we'll hear in just a moment for just a few seconds. But some of those sounds are actually the images. And so the next part of the record, or the record cover, is telling us, hey, look at those sound waves. There are certain sound waves you have to do something special with, okay? So up at the very top here, we have this very rapid oscillation here. So this is kind of like a marker for a beginning. So what we're going to see is this whole pattern is essentially going to repeat. So if you were to play the records and you were listening to the image part of it, you would hear this tone. It actually sounds like a beep, and you would hear that multiple times. So that's basically saying, hey, here's the start of our image. And then when you hear the next beep, that's the start of the next image. And what we're seeing here, this is basically a graphical representation of the sound wave, but it's got a very distinct pattern to it. So you'll note that we get this little packet of information, then there's a dip, and then another packet of information, a dip, another packet of information, and that same dip again. So there's a repetitive pattern, which should be a clue to, hey, there's something going on here. It's not just random sounds here. So each one of these three patterns that we see here, you notice there's a binary sequence above it. This is representing 1. This is 1, 0, so that's 2. This is 1, 1, so that's 3. Down here, it's saying, here's 1, here's 2, here's 3. So for this particular packet of information, what you should do is then take that packet and basically draw it out, but you want to have it set up to where when you finish drawing it, your next packet of information isn't lying right over top of it. We need to offset it a little bit. Draw the next one, offset it, draw the next one, okay? There's also a binary value up here to show, just how long each one of these little packets of information is, which turns out to be about 8 thousandths of a second. But now, what do we do with those individual lines of information that we're drawing out? So the middle and bottom portions really illustrate that for us. So now, this bottom portion, we're going to take these lines, which have been exaggerated for clarity, and we're going to draw them more realistically. So right here is our first line. It's kind of hard to see, but we've got our rectangular outline. Right here is the first line that's being drawn. And then when we get to line number 2, we scoot over a little bit and we draw the second line. We get down to the bottom, we scoot over a little bit, we start back up at the top, just like this one starts back at the top. We draw line 3. In fact, there's the label for 1, 2, and 3 right there. And you keep doing this until you get to this binary value, which equates to a value of 512. That's essentially saying, hey, you're going to do this 512 times. And once you're done, that's the end of that particular segment. And what you should then see is another one of these beeps come along. Okay? So once you get to 512, you're basically done with the image. Okay? And this actually takes about 4.3 seconds for each image if you play it at the correct speed. Now, if you're familiar with the old style televisions, which were very prominent in the 1970s when these records were created, you remember this style of TV. We didn't have the nice LCD screens. We had the cathode ray tube televisions. So a cathode ray television works in the same way, except that it uses an electron beam to cause the screen to glow wherever that beam hits. And so the beam would be directed by magnets down here. It would start on one side of the screen, draw across until it hit the edge of the screen, and then very rapidly it would switch back over, go down slightly, draw line number 2, switch back over, go down a little bit, draw line 3 until it drew the entire image. And it would do that about 30 times a second. So that's essentially what we're doing here. We're having our ET friends actually drawing out the image just like an old CRT television would do. And if they get things right, as indicated by this other symbol, then the very first image that they should get is a circle. So if they don't have things timed quite right, then maybe their circle's going to be squashed, or maybe it's going to be really stretched tall, so they can then alter their playback speed or alter other parameters until they get that nice circle. But once they've got that circle, then they know they're onto something and they can decode the rest of the images in the same way. So we're almost through here. I just want to give a few more illustrations. We'll talk just a moment about the pulsar map, and then we're good, because I don't want to spend or take too much of your time this evening. There's a really nice YouTube video, and I can provide the link afterwards. I believe that this video is going to be recorded, and we can probably post the link to that YouTube video as well. But this is where someone has taken the actual audio recordings from the image part of the golden records and decoded them in real time. As in, let's say I actually had one of those golden records and I had my little turntable. I set my record on there, got it rotating at the right rate, and put my stylus on there, started seeing the waveforms, and started decoding those in real time. This is what we would see. So for the very first image, that circle, I've taken that little snippet of the video and I've slowed it down by a factor of 5. So it would actually take about 21 seconds to decode. You're not going to hear anything in this particular version, but what I want to show you is just how this is working. So right now, we're decoding a line right down through here, which starts out very white at the top and goes down to gray. This is essentially the information packet for that entire line. So this is essentially representing the very top part of the image. This is the very bottom part of the image. So the taller the wave packet is at a certain point, the brighter that part of the image is. So right up here is white. That is represented by this high peak. And then as we get dimmer and dimmer, we're down into the grays. We've leveled out, and then dips down to basically 0 here, and that's where it's black, right down at the very bottom part of the screen here, okay? So everything looks pretty much the same. This is the next line that's going to be drawn, the next line after that, and the next line after that. So let's start drawing that circle, and you'll see the difference. All right, so now we are in the process of drawing part of our circle. So we started up bright, getting down to the gray, then all of a sudden we dip down to black. Then we come back up to gray to draw the inner part of the circle. Then we dip down again to black to draw the outer edge of it, and then come back up to gray. And that's what we're seeing here. So this little dip right here, there's the this edge of the circle. Here's the center part of that image, which is gray. And then we have the other part of the circle, the other edge of that loop. So as we draw the circle more and more, and we see wider and wider parts of the circle, you'll see that these little dips actually spread apart. So let's go ahead and do that. So now we're almost to the widest part. Now we're at the widest part. Our dips are right here, right over here, so they've really spread it far apart. And as this loop comes on around, it's drawn some more, and it comes around, and it's trying to intersect itself, we'll see those dips come back together. Okay. So now they're starting to come back together. You can see them right here. And as the edge of the loop gets closer and closer to completing, the dips get even closer until they merge and then disappear. And now we're back to simply doing gray lines. So now we don't have those dips anymore. So that's what we're seeing here. Okay, and again, this is the calibration image. So now just to give you an idea of what this looks like in real time, what ET is hopefully going to see, let's scoot over to our next slide. Now this time we're going to have some sound. I'm going to turn my sound down just a little bit, but you should hear every now and then a beep, and you should hear what sounds like a bunch of static. But that's the sound of these images, and we're taking that sound and we're converting it in real time to the image data and drawing those images out. So those high-pitched beeps that you hear, that's that oscillation that we see on the front of the golden record that says, hey, here's the start of your image. And you can actually watch the data being drawn out by seeing all these dips. So every time there's a dip, that's a black pixel in the image. Here's a nice view of a frog. This is what a frog looks like in sound waves. Here we have, I believe that is a crocodile or an alligator. And we have bird of prey. So again, you can go to YouTube and you can check this out. You can see every one of the images decoded. So please do that. Let's see. All right, so the final thing on our cover, and this is about where we'll end, is our famous pulsar map. So I just want to take about 5 minutes to describe what a pulsar is and how we're going to figure out where we come from. So let me go ahead and put up all of my information here. So what we're seeing here, all of these little lines converge to a point. That's our location, okay, in our solar system. This long line here terminates over here. That is representing the distance to the center of the galaxy, which is about 25,000 light years. Now the rest of this, these lines are, there are 14 of them. They are showing the essentially the directions to pulsars, 14 pulsars that we know of. There are actually a lot more, but these are 14 that we had some distances to. And we give a couple bits of information. Let me zoom in just a little bit more here. So you see that, for example, on this one, there's this long line, which then terminates right there. That's telling essentially how far that pulsar is from the Earth or from our location. Remember, this ET will have an idea of how long that's actually describing based on this distance here, described by this line going from this Earth to the center of the galaxy. Now, at the ends of these lines, sometimes right next to it, is a binary sequence. And that binary sequence is just going to tell us how rapidly these pulsars pulse. So that as ET is looking for us in the galaxy, they're going to find these pulsars, they're going to measure how fast they pulse, and they're going to say, aha, I found a pulsar that actually matches the pulse rate indicated by this particular pulsar here. So if I can find all the other pulsars, they'll essentially point me to where this probe came from. Okay. Some of these, like this little guy right here, has a very short line because it's only about 120 light years from us, whereas this pulsar up here is about, I believe this one is about 4,500 light years from us. So this is essentially giving us a distance and telling us, hey, which pulsar to look for. Okay. Okay, so again, the binary tells us about the pulse rate of these pulsars. So what is a pulsar? It is a large star that has died in an explosion, and the core of that star has collapsed down to create a very, very compact, very dense ball of neutrons. We're talking about something that is about 700,000 times as massive as the Earth, compressed into a ball only about 10 miles wide. So these are incredibly dense objects. They typically have very, very strong magnetic fields. And because their parent stars were rotating before they died, when these cores collapse down, they are also rotating, but they spin up as they collapse down, just like an ice skater that has her arms out. When she's spinning and pulls her arms in, she spins faster. Same thing with the cores of these stars. Okay. The pulsar, as it's rotating, its rotation axis is often misaligned with its magnetic axis. And as the magnetic axis sweeps around, it interacts with charged particles, which generate different forms of light. And if we happen to be in a good spot, we may see that pulsar magnetic field sweep around and actually point towards us and essentially emit the light in our direction. And every time it sweeps around, we see a pulse of light. So that's how pulsars get their name. Pulsars are incredibly regular. They're comparable in some cases to atomic clocks. Here's a really nice example of a pulsar. Over here we have the Crab Nebula, which is a star that we observed to explode about a millennia ago. But right at the very center of this nebula is the core of that star. In fact, right here, this is a movie made showing that pulsar actually pulsing in visible light. You may say, okay, that's pretty cool. I'd love to be able to see that. This movie has actually been slowed down by a factor of 50. This pulsar, called the Crab pulsar, it spins about 33 times a second. It would be spinning so fast that your eye wouldn't actually see the pulses because it's just spinning way too fast. But we can detect those pulses in radio light and in other cases, as we see here, other forms of light like visible light. Here's kind of an illustration of a pulsar, and I'm going to have a little bit of sound with this as well. So what you're seeing really rotating around here is the magnetic axis sweeping around and pointing towards us. Every time it points towards us, we hear that click. Okay? That's a little bit of radio light coming in. It's like a little fraction of a second of static. Okay? So this is an actual recording of the pulsar B0329 plus 54. These are basic coordinates. And this pulsar rotates about 1 time every second. Okay? So if an extraterrestrial is using a radio telescope and takes that radio signal and converts it to sound, you can actually listen for these pulses. Let me give you a couple of other examples. This is the Vela pulsar, which is one of those pulsars that is on the pulsar map. In fact, the previous one was also one of those. This one rotates about 11 times. So you get a very rapid pulse rate. And then finally, one more. This one is not. This is pulsar B1937 plus 21. It actually spins over 650 times per second. The pulsing is so rapid that it actually sounds like, essentially like a mosquito flying around. It doesn't even sound like pulses anymore. So, just imagine a ball 10 miles wide rotating 650 times a second. That really is kind of mind-boggling. Okay. So those are examples of pulsars. So they permeate our galaxy. They often have very unique rates of rotation. So if you can find a pulsar that matches, or pulsars that match the descriptions on the pulsar map, then you might have a good chance of figuring out just exactly where these probes came from, because you can use those pulsars to triangulate our position. And then finally, to answer when did the records originate, we mentioned this earlier, but there is a spot of uranium-238 that's been electroplated onto the record cover. It's radioactive, so it decays over a very slow period of time. So that uranium eventually converts into lead-206. But since we know the decay rate, and ET is likely to know the decay rate, then we should they should be able to determine just how long it's been since this record was launched into space. So to give you a visual of this, here's our original sample of radioactive uranium-238. We've got a certain amount of particles there. One half-life later, which for this particular element is about 4.5 billion years, half of those particles should have decayed into lead. And then another half-life, another 4.5 billion years, half of those remaining particles should have decayed into lead as well. So in this view, one half-life later, we're left with half of our original sample. 2 half-lives, we're left with a quarter. 3 half-lives, we're left with an eighth. And so you can see that as our sample decays, the original amount goes down, but the amount of the byproduct, or what we call the daughter particles, increases. And so by comparing these ratios, you can actually determine how long that sample has been there. So this will hopefully give an idea of when this record was launched into space. So to close, again, to quote Carl Sagan here, this is actually pertaining to the golden records that were launched aboard Voyager 1 and 2. So the spacecraft, as in Voyager 1 and 2, will be encountered and the record played only if there are advanced civilizations, advanced spacefaring civilizations in interstellar space. But the launching of this bottle in the cosmic ocean says something very hopeful about our life on this planet. So with that, I will bring it to a close, and I appreciate everybody sticking around. Sorry we went over a little bit of time there, but I hope that you all enjoyed this and learned a lot about it, because as I was doing a little bit of research on some of these aspects, I learned a lot as well. And I'm again thankful for being here this evening.
Thank you so much, Dr. Teach. This was so informative. It really puts the work that's in our galleries in a new light. You can appreciate the science and everything behind what we're seeing in the gallery. So we really appreciate it. Again, you can see Jitish, Kallat, Return to Sender in our galleries on view until October 12th. We are open, and you can reserve your advanced time tickets on our website, fristartmuseum.org. We do have a few questions. If you have a couple moments and want to hang around, we can answer those. Robert asked if the Voyager was moving towards any known bodies.
They are not moving towards any particular, let's say, star system. You can actually look up a map of where they are right now, like in the constellations. They're not projected to really pass super close to any other star systems. There's like a red dwarf star that I think it's Voyager 2 is going to pass by, or pass within a light year of, in about, I want to say it was like 40,000 years or so. I can't remember. But they weren't on any particular trajectories or assigned trajectories after their last encounter. So, for example, Voyager 1, with its flyby of Titan's gravity actually bent its trajectory down a little bit with respect to the plane of the solar system. So, no, I'm sorry, up with respect to the plane of the solar system. So if you were at Voyager right now, you would see kind of the solar system moving away from you, but you would be getting higher and higher up. Whereas Voyager 2, its encounter over Neptune actually sent it down below the plane of the solar system. So it's kind of looking from the bottom up. So it's not projected that they will get really close to any other stars that we know of.
Okay. Once the 2 probes traveled beyond the heliopause, did their speed reduce, or does the radioactive power source provide pretty constant propulsion? Drew asks.
So the radioactive power supply is solely for electric generation for the instruments themselves. On board Voyagers 1 and 2, they had, I think the tank was 28 inches wide, so about like that. But it was filled with hydrazine, and that was a thruster for doing minor course corrections. So their initial speed, let's say from the Earth, was due to their launch on the Centaur rocket. And then once they got to Jupiter, Jupiter accelerated them to an even greater speed. And then as they moved out farther away from the sun, their speed would gradually decrease because the sun's gravitational pull is decreasing. Then once they get to Saturn, Saturn speeds it up again, not quite as much, but gets it out to Uranus. Uranus then speeds it up again to get it out to Neptune and so forth. So once we've left Neptune, we're getting pretty far away from the sun, and so the speed is very, very gradually going to be decreasing because the gravitational pull of the sun, even though it's still out there, is going to very slowly decrease. So it doesn't have any active propulsion on it. It's just been using the initial rocket launch and then gravity to get it to its velocity that it's at now. So the propellant that it had on there was just basically for turning it, or for they would fire it for a very short period of time just to kind of change the angle at which it was moving. But you know, if we could put big thrusters on there, then we could have put it in orbit around Jupiter, and then when we wanted to, then left and gone to Saturn. But when doing these gravity assists, that's why you can't stay in orbit. You've got to, because you're using the gravity to get you to the next thing. So yeah, that's the long roundabout answer for saying that they are very gradually slowing down, but they're not getting any active propulsion.
All right. So a couple questions about the record. How would extraterrestrials know what a second is?
So that's one of the things. So the very first part, so when we were talking about the hydrogen atom, we had, when I say we, the folks that created this and were designing this had to figure out a way to say, you know, establish some sort of a time element, you know, because a lot of this decoding the records is going to be based on how fast they're rotating and whatnot. So we had to get everything in terms of something that would be universal to everybody else. So we are expressing this transition time of this atom in terms of seconds, or in this case, 0.0 billionths of a second. But for an extraterrestrial, you know, for them, time, you know, they may be able, you know, to, I don't want to say experience time, but they may use a different a method or a unit for time. So their second may actually be like 0.42 of our seconds. Okay, so what we're saying here is that we're not saying, okay, now take this value, which is 0.7. We're just saying, you see how long it takes this hydrogen atom to transition from this state to this state? That's going to be your time unit. You can call it whatever you want to, but it's a certain amount of time. Everything else we're going to express in this one little unit of time. Okay, that kind of makes sense?
Yeah. So this hydrogen diagram at the bottom is really to help establish a common time for the record.
Right. Yeah. And so, you know, it's that time that it takes that hydrogen to do that transition, that's independent of anything that we're going to do to it. I mean, it's going to take that amount of time. And it doesn't really matter how you measure it. It's always going to be that certain span of time.
So if we were to send out another golden record in 2020, what would you imagine we would do differently?
Oh, that is a really good question. I mean, we've certainly had a lot of technological improvements. I think that we would definitely try to pack a whole lot more information in there, a lot more videos, try to just essentially create a better time capsule. And, you know, technology has really progressed. We've learned a lot more about, you know, for example, pulsars. We've refined distances a lot more. We might be able to have a little bit easier method for extraterrestrials to try to figure out our location in the galaxy, because those pulsars, along with our solar system, are all moving at different rates through our galaxy. And so, you know, it was a good way to help figure out where we were, but, you know, there might be other methods for, you know, giving our location. But, you know, to give a really good answer, and I'm kind of babbling at this point, I'd really have to think hard about that. And there are some really creative people out there that would say, hey, you know what, we should really include this on you know, this giant DVD now. So I'm sorry I can't give a better answer to that, but yeah, that's a really tough question, and I would love to hear some ideas that people had.
Well, we've certainly made a lot of scientific discoveries since 1977, so I'm sure
Definitely have, yeah.
it would look a lot different. Well, thank you again, Dr. Teets. Thank you all for joining us, and we hope you have a great evening.
Thank you.
You can find out about more programs at fristartmuseum.org. You can visit Dyer Observatory to check out the star party, which sounds amazing.
Can I just make one interjection?
Yeah.
So make sure to check out the Dyer Observatory's website. So we unfortunately are still currently closed to any public visitors because of the pandemic. So we're trying to move all of our events to an online format. So, but definitely check out our webpage for updates on virtual stuff. And also if it looks like we might be having in-person events, we'll put all of our updates up there.
Right. Well, thank you so much. Thanks again, everyone, and have a great night.
All right, thank you.